Namaste dosto. Imagine you and your friend are each tossing your own coin. No peeking or influencing each other's tosses. Now, whether your coin lands heads or tails, does it change the chance of your friend's coin landing heads? Obviously not. That simple example brings us face to face with the idea of independent events in probability. So, what does independence mean in math terms? Two events, say A and B, are called independent if the occurrence of one does not affect the chance of the other happening. Another way to say this is that the probability of both A and B happening together equals the product of their individual probabilities. In formula language, that's P of A intersection B equals P of A times P of B. Let me repeat that slowly. P of A intersection B equals P of A times P of B. And here's an interesting point. Independence is symmetric. If event A is independent of event B, then event B is also independent of event A. Of course, assuming both have probabilities that are defined. Why is this important? Well, in probability models, especially when dealing with random processes, independence means one event happening doesn't interfere with the other. It's like saying the roll of one die doesn't affect the roll of another. But be careful. Independent events are different from incompatible or disjoint events. Incompatible events cannot happen together. So the probability of both occurring, P of A intersection B, is zero. This zero product almost always contradicts the independence condition. Because if the probabilities of A and B are not zero, their product won't be zero. So, disjoint events can never be independent. If you look at a Venn diagram, picture two circles overlapping. The area where they overlap represents P of A intersection B. The total areas represent P of A and P of B individually. When the overlap equals the product of these two probabilities, the events are independent. This visual helps cement the concept. Continuing from our basic understanding, now let's bring in conditional probability, a powerful tool. Suppose we know that event B has happened and that its probability, P of B, is greater than 0. Then we can look at the chance of a happening given B has occurred. This is written as P of a given B or P of a vertical bar B. By definition, P of a given B equals the probability of both A and B happening together, divided by the probability of B. Formally, P of a given B equals P of A intersection B divided by P of B. Let's repeat that slowly. P of a given B equals P of A intersection B divided by P of B. Now, if A and B are independent, having B happen shouldn't change the chance of A. So, P of a given B must equal P of A. And by the same logic, P of B given A equals P of B. When you combine this with the conditional probability formula, you see that P of A intersection B must be equal to P of A times P of B. This equality is both necessary and sufficient to prove independence. In simpler words, to check if two events are independent, see if their joint probability equals the product of their single probabilities. Think of this as a flow. If you know P of A intersection B, you can find P of a given B by dividing by P of B. If this equals P of A, then independence holds. These links form a quick verification tool, especially helpful in exam problems. Imagine a flowchart here linking P of A intersection B, P of a given B, and independence. It helps make the logic crystal clear. Alright, time for a quick pause. Think, if P of a given B is different from P of A, are events A and B independent? Exactly. No, they are dependent in that case. Let's wrap this up before moving onwards. Now, what happens if there are more than two events? Let's say 3 or even more. When dealing with events labeled A1, A2, A3, and so on, these events are mutually independent if every possible pair and combination satisfies the independence property. For just 3 events, A, B, and C, they are mutually independent if the following all hold true. First, the probability of A and B happening together equals the product of their probabilities. So P of A intersection B equals P of A times P of B. Second, the same must be true for B and C. P of B intersection C equals P of B times P of C. Third, for C and A, P of C intersection A equals P of C times P of A. Fourth and very importantly, The probability that all three happen together equals the product of all their probabilities. Formally, P of A intersection B intersection C equals P of A times P of B times P of C. Notice that just checking pairwise independence, that is, independence between every pair, is not enough to confirm mutual independence. The triple intersection condition must also be satisfied. This is why it's very important to test all combinations when verifying independence for multiple events, especially in real-life probability problems involving several random factors. Picture a Venn diagram with three overlapping circles labeled A, B, and C. Each overlapping region has its own probability, and we check if products match joint probabilities accordingly. Keep this multi-event approach in mind. It's a crucial step up in understanding probability. Welcome back. Let's apply the definition of independence using a simple example. We are given three values. P of A equals 0.4, P of B equals 0.5, and P of A intersection B equals 0.2. Our goal is to verify whether events A and B are independent. Step 1. First, compute the product P of A multiplied by P of B, that's 0.4 times 0.5, which equals 0.2. Step 2. Now compare this with the given value of P of A intersection B, which is also 0.2. Since both values match perfectly, this confirms that the two events behave independently. Conclusion. Because P of A intersection B is equal to P of A multiplied by P of B, we can confidently say that events A and B are independent. Now, let's contrast independent events with disjoint and dependent events, because this is where many students get confused. First, disjoint or mutually exclusive events can never be independent. Why? Because for mutually exclusive events, the intersection P of A intersection B is 0 by definition. But for independent events, the product P of A multiplied by P of B is never 0 unless one of the events is impossible. So the two ideas simply cannot coexist. Next, remember that the size of individual probabilities doesn't tell us anything about dependence or independence. Even if P of A is very high or very low, that alone doesn't decide independence. The intersection rule must be satisfied. Another common misconception. Students often assume that if P of a given B happens to equal P of A in one situation, then the events must be independent. But this must be checked using the full definition, not just a single observation. Finally, independence must always be established analytically, using the formal condition P of A intersection B equals P of A multiplied by P of B, not based on visual intuition or assumptions. Let's wrap up everything we've learned about independence in probability. First, the core definition, P of A intersection B equals P of A multiplied by P of B. If this condition holds, the events A and B are independent. Next, through conditional probability, independence also means P of A given B equals P of A, and P of B given A equals P of B. So knowing that one event has occurred does not change the probability of the other. For three events, A, B, and C, independence becomes stricter. All pairwise intersections and a triple intersection must satisfy. P of A intersection B intersection C equals P of A multiplied by P of B multiplied by P of C. Verification requires exact equality. Not approximation, not estimation. The numbers must match perfectly. When dealing with multiple events, we must check both pairwise independence and mutual independence. One does not guarantee the other. Independence also means that information about one event gives no new information about the other. And finally, remember this crucial point. Disjoint events can never be independent because their joint probability is 0.